So here's a very basic one to start with. We've got a triangle there. We've got the vector from m to n. So if we have any vector, we can always write the position vectors of that. So the position vector for the point m would be m, and the position vector for the point n would be n. So to go from m to n, you could do that by going to the moon. Minus m, because that would get you back to the origin, and then plus n, because that would get you to n. And then n to m would just be the opposite of that, minus n plus m, or just m minus n. So now we're going to add a point P right in the middle of m to n. What is the position vector O to P in terms of m and n? So how could we get, starting at O, get to P if we're only allowed to walk in these directions? So this might be maybe a robotics problem, where you've got a robot that only travels in two directions. You're starting here, you want to end here, and it can only travel in the directions of m and n. How could you get him there? Well, if you wanted to go from O to P, does it make sense that you could get there by going from O to m and then going halfway from m to n? Now that's not traveling only in the directions of m and n, but that's the idea. Now as far as that idea, well, we already know that m to n was minus m plus n, because we figured that out in part A. And with those vectors, if we combine our like terms, it says go half in the direction m and half in the direction n. And that will get you from O to P. So now drawing that out, what does it mean to go half in the direction of m? That would be going halfway here. And half in the direction n would be taking this n vector and doing half of it, and sure enough, you end at the point P. Putting this back into our coordinate geometry, let's say this was the point 5, 8, and this was the point 6, 4. If you wanted to find the point P, in the past you would have used your midpoint formula. You would have added the two things up and divided by 2, and that would have been no problem. Now, this is saying that we can put this together, and I could also write this as this way, right? Well, all that's doing mathematically is m, I said, was 5, 8. So 5 in the x direction, 8 in the y direction, plus 6, 4 can you see that that's exactly the same as your midpoint formula? Because all you're going to do is add your x coordinates together, add your y coordinates together, and multiply them by half. Oops, not a fraction. And get your midpoint. But again, the nice thing is you can work abstractly with the vectors, get a result, and then just apply your results to your coordinates to begin with. And what you're going to be able to do is solve some more complicated questions that wouldn't be easy with our old coordinate geometry. Or this will make them hopefully easier. So here's the first one. It's just a midpoint idea. So you've got three position vectors, A, B, and C. P is the midpoint from A to B. And Q is the midpoint from B to C. What we want to find is what is the position vector of point P and what is the position vector of point Q. That's going to be very similar to what we just did in the example before. But now you can go from P to Q using only the directions A, B, and C. How would you do that? What would it look like? So first of all, if you wanted to go from O to P, again, the picture makes sense. I want to start at O. I want to end at P, which is on the green line. How do I get there? I go from O to A, and then I go halfway between A and B, because it's a midpoint. And A to B is just the same as going backwards on A and then back plus B. So that's how I have the minus A plus B. Combining those things together, you get 1/2 A plus 1/2 B, which is what we saw before with M and N. Similarly, you can find OQ. It's going to be 1/2 B plus 1/2 C. Now that you have position vectors of P and Q, how am I going to get from P to Q? Well, I'm going to start at P. I'm going to go back to the origin, and then I'm going to go from the origin to Q. So P to O is just going to be negative 1/2 A and negative 1/2 B, just the negative of what we found before. And then adding O to Q. And we find out to go from P to Q is just 1/2 A plus 1/2 C. I think we have time to do one more. So we have a regular hexagon. And if you have a regular hexagon, and you know that OA is A and AB is B, does it make sense if I would draw all those radiuses that you end up with a bunch of vectors that are all the same length? Because a hexagon, when it's split up, makes a bunch of equilateral triangles. So now, having only those two direction vectors, we can say everything else. How could I get from O to B using only A's and B's? So So I'm starting at O. I want to get to B. Can you see that you can go along A and then add B? So it's just going to be A plus B. From B to D. How could I get there? Well, I could go from B to C. Can you see that that's the same as a negative A? And then I could go from C back to O, and that's the same as a negative B. And then I could go from O to D, and that's another negative A. So on our diagram, we could draw a route plan using parallel vectors, and you can see that it's going to be negative 2A minus B. Another way to look at it, okay, that was one route plan. Another route plan says, well, what would happen if I started at B and went this way first and then went 2 in that direction? That would be another route that would give me negative B minus 2A. If you wanted to go from C to F, starting at C, going to F, you can see that that's just negative 2B. Now, the power of this says if you know where the origin of your hexagon is and you know 2 of the coordinates, you can use vectors to quickly write out all the other coordinates and where they're going to be. Whereas using the math you had before, you might have to take a step back and think, okay, how am I going to set this all up?